Alright, so here are the solutions for these practice problems, getting ready for our quiz on Wednesday. First one here is a computer that's sliding down a desk that's slanted at a 10-degree angle. Here's my computer. We're told that the computer has a mass of 1.5 kilograms. And safe to say, right, that this computer is accelerating down the slope, right? It's not going to be traveling up the slant of the desk. So the acceleration is in this direction, and the F net is also going to be in that direction, right? Because acceleration and F net are related to each other directly. So I'm going to draw a free body diagram here for my computer. We're going to have gravity going straight down. We'll have some normal force, and then there's going to be a friction force acting up the ramp. Give those some labels. Some of you are probably like watching this in double time. Yeah, been there, done that. Free body diagram. And then I'm going to go ahead and draw in my components here for FG. Right here we're going to have FGY and then FGX. Label those. And FGX. And this right here is my angle of 10 degrees. So the original question is, what is acceleration, right? So from this we know that we're going to need to use eventually F net equals ma. That's going to be the key to this. So we've already determined the direction of F net, right? It's down this slope. So the next logical step is to ask ourselves what forces are also acting in this plane, right, along this direction of acceleration in F net. And of the forces that we have, right, Fn is not acting in that direction, right, it's acting perpendicular to that direction. Same thing with Fg, and these are actually going to be balanced. They're going to be the same size because the computer isn't floating up or down the desk, it's just moving along the desk. So the two forces that we're going to be concerned with here are the friction force and the component of Fg that's parallel to the direction of motion. Those are both, as you can see here, working in the same direction, same plane as the movement of the computer. And of the two of these, right, if we imagine that they're, both connected to the computer and they're pulling on the computer, and the computer is moving down the slope, it stands to reason that FGX is pulling harder on the computer than the friction force, right, if we imagine them in tug of war. So we can say that the FGX is going to be greater than FK. And that if we subtract, right, the greater value from the lesser value, we're going to get F net. Right, the difference between these two that we can convert to acceleration. So we arrive at F net equals FGX minus the friction force. So now, right over here, this was FGX and this was FK, just thinking about, in terms of which has to be bigger in order to create this direction of acceleration. So now we have this equation that's ultimately going to be key to solving for acceleration, but we have to first solve for these two values, which we have some trig and some general equations that will help us. FGX, right, if we look at our triangle here, is the opposite side, and FG over here is our hypotenuse. So the sine of Uh-oh, my pen's not working. The sine of, hold on, let's see if I can get this to work. Uh-oh, Oh, it finally caught up. There we go. A little lag there. Let's try this again. FGX is going to equal the sine of 10, right? It's the opposite side, times FG, right? The weight of the thing. And we can calculate FG using, right, mass times 9.8, or little g. And the mass was given, so we're going to have, it's a 1.5, whoa. Technical difficulties here. Let's see if we can get this to work again. It's a 1.5 kilogram computer times 9.8 meters per second squared. So the force of gravity on this thing is going to be approximately 14.7 newtons. We can plug that in up here, and if you multiply 14.7 times the sine of 10, you should get approximately 2.55 newtons for FGX. Okay, so we've got our first term here. Now we need to solve for FK, and we have this handy equation here, right? Mu K times Fn. A detail I forgot in the original problem, we were given that mu K for this surface equals 0.065. No, that's not right. 0.062. Sorry, it's a 2 there, not a 5. So we have this value here, mu K, and we can solve for Fn, right? Remember, Fn in our free body diagram equals Fgy, right? Since Fn equals Fgy, and using our trigonometry, this is the adjacent side, so it's going to equal the cosine of 10 times Fg, which we know to be 14.7. The cosine of 10 times 14.7 should be about 14.5, 14.47 to be exact. We plug that into our above equation. Fk equals 0.062, right? That's given in the problem, times 14.47. And you should get that the friction force is going to equal about 0.9, 0.89, we'll call it. So we now have, right, we've found our friction force, which is going to get plugged in up here, right? And we've also found our x component of Fg. Cool, we can now solve for Fnet. Once we have Fnet, it's pretty much a cakewalk into the finish line here for solving for acceleration, right? So we have our original equation, Fnet equals Fgx minus Fk. So using the values that we determined, Fnet is going to equal 2.55 newtons minus 0.89 newtons. Fnet will equal 1 point, 1.66 newtons. There we go. Calculator error there. We then plug in, right, 1.66 newtons to Fnet equals ma. We've got the mass here of 1.5 kilograms times acceleration. Divide both sides by 1.5. The acceleration of the computer is about 1.1 meters per second squared. Okay. So moving on to the second problem here, Pinewood Derby car coming down a ramp. Our ramp in this case is at an angle of serious technical difficulties tonight. All right. Angle of 53 degrees. Finally, 53 degrees. And the cart itself has a mass of 1/2 kilogram. And we're told that because there are wheels on the cart, we can assume that this motion is essentially frictionless, right? So that's an important detail. For our free body diagram, we, of course, have gravity straight down. Get rid of that dotted line. And then we're going to have the F normal, right, Fn straight out. Gravity can be divided into components, of course, where the y component is counteracting the normal force, and the x component is going to be pointed down the ramp. So this is our ramp here, is in the blue. So if this is the way that we draw it, we will have our 53-degree angle up here. There's 53. This is FG. Here's FN. And this is the Y component of FG, and here's the X component. So the cart is accelerating down the ramp, so that means that F net must also be down the ramp. We want to identify what forces are acting in the same plane along the same line as F net. In this case, it's only the X component of FG, right? So we're only concerned with the FGX. In fact, right, since there's no friction force like there was above, our F net is just going to equal FGX, right? The Y component of the gravitational force is equivalent to the normal force, but we won't have to solve for that, right? Because we don't have to solve for gravity. So the X side here is opposite the angle. FG is the hypotenuse, right? So we could solve for FGX using our sine angle of 53 degrees times FG. In this case, FG equals 1/2 of 9.8, right? This is just mass times little g, right? So FG will equal 4.9 newtons times the sine of 53 degrees should be 1.94 newtons, I believe. And that's going to equal our F net. So we have that F net, 1.94 newtons, equals our mass times acceleration, right? Our mass is given to us in the problem. It is 1.5 newtons. So we divide both sides by, 1.5 kilograms is going to equal our acceleration. Note, kind of a sticky point here I noticed in class was people were confusing mass and the force of gravity, right? You can't relate the force of gravity here to the F net, right? Because you'd be dividing something in newtons by another thing in newtons, so your answer should be unitless or in newtons, so that's not going to work out well. You have to divide by kilograms. And this really comes from the fact that 1 newton, right, a newton equals a meter times a kilogram over a second squared, right? So if you think about it, a newton divided by a kilogram, as we've done here, see newton divided by a kilogram, the kilograms will cancel, and you'll end up with units of meters per second squared, right, which is what we want for acceleration. So watch out, make sure that you're using FG when appropriate and mass when appropriate, okay? The answer here, right, acceleration is going to be around 1.3 meters per second squared, all right? Hopefully that helped. Happy studying. I'll be around on Tuesday night if you need extra guidance.